So at the end of last class, I started to talk to you about Incidence Hopf algebras. And so let me just remind you what we were saying. So the setup is the following. We start with a hereditary family. And this is a family of finite intervals which is closed under two things. It should be closed under taking intervals, taking subintervals, and it should be closed under taking direct products. Okay. And I'm going to call this family P. So the first property says that if you take an interval in P, then any subinterval should be in P. And the second property says that if you take two intervals in P and you take the direct product, then that should be in P as well. Okay. So we start with a hereditary family, and we also start with something that I didn't define for you yet. And it's a reduced congruence, and what that does is that it's going to be an equivalence relation on P. An equivalence relation on P such that certain properties hold. Okay? And we will talk about exactly what that means. But then the proposition is that if you have these two things, that's going to give you a Hopf algebra. Okay. So if we have this, then if we define H of P to be the K-span of the equivalence classes, then this is a Hopf algebra with the following operations. The product of P and Q is P times Q. The coproduct of P is the sum over the elements of the poset of subinterval from 0 to P, tensor subinterval from P to 1. The antipode is sum over n greater than or equal to 0 of sum over all the chains from 0 to 1 that have n steps, and then we get minus 1 to the n times the product of the intervals from x0 to x1, from x1 to x2, up to xn minus 1 to xn. Okay, so that's the antipode. The unit is going to be, I'm realizing I wrote this wrong last time. So the U of 1 is going to be the poset of one element. I think last time I wrote that it was the empty poset. Did I do that? Yeah. So that's not what I meant. What I meant is that U of 1 is the poset of one element. And that is what I want because the poset of one element is the one such that P times that poset is P. And the co-unit is, yeah?
So it doesn't really matter what that point is, as long as it's one. It could be anything, so P cross the singleton would be isomorphic to P.
Uh-huh.
It won't matter what that point is. What is there some?
Let's I mean, let me. So, I think it's a valid point that there might be different posets of one element, and they're all isomorphic, but they might not be equivalent. At least with what I've defined so far. So, let's just assume that all the posets of one element are equivalent. Okay, and if so, then this is actually well defined. So epsilon of a poset is going to be 1 if the poset is a single element and 0 otherwise. Okay? And so this is the definition of an incidence Hopf algebra, something that arises like this. Okay? And so what I wanted to do today is, so first of all, let me make a point that this is a very important definition, and we're gonna spend the next couple of classes looking at different examples of this, because we will see that there's a lot of very interesting Hopf algebras that arise from this construction. Okay? And so let me first give you a quick argument for why this is actually true, that this gives you a Hopf algebra, and then we will just see tons of examples. Any questions or comments on this definition before we continue? Yep.
I'm curious. I guess I don't understand Stephen's question about how you could have two different posets that weren't equivalent on one order. And there's no way that you could have an incongruous order relation.
So let me repeat the question. The question is going back to the question is this well defined? U of 1 is a poset of one element. The thing is that this starts with a hereditary family, and so it's some family of posets, and a reduced congruence, which is some equivalence relation that I'm calling twiddle on P, such that blah blah blah. Okay. Last time when I wrote this down, I said the equivalence relation is usually going to be isomorphism, and if that's the case, then clearly every point is going to be isomorphic to any other point. I mean, any two intervals of one element are going to be isomorphic. The problem is that there might be more general reduced congruences where we might actually want to say that even though two posets are isomorphic, I don't want to consider them equivalent. And we will do that later on. And so I'm just saying that to make this definition precise, to make this definition correct, I'm going to assume that all posets of one element are declared to be equivalent.
Is that going to fall out of whatever we decide for each kind of equation?
Yes. Yeah. Okay. So let's make an argument for why this is true. But the argument is basically that we already did this, more or less. Okay? Why is that? Because We already did this. For P is the collection of all finite intervals. Well, let me be a little bit more precise. Let me say for P equals this and this equals equivalence, isomorphism, poset isomorphism. We already talked about this object. We defined the product in the same way, the coproduct in the same way, and we proved in class that this is a bialgebra. We checked that this is a bialgebra. Okay. We checked the axioms, it was fine. And I just want to argue that the exact same proof works here. The same proof works here. You really don't have to do anything about that, okay? And so I'm asking you to trust me that what we did earlier works to prove that that we have this bialgebra structure. But now the question is about the Hopf algebra structure. And so what we're missing for that is the antipode. And if you look back, actually, I didn't actually talk about the antipode for this. And so what I want to do is compute that antipode. Okay? So let's actually compute the antipode. And so I'm going to basically make the same argument as in Takeuchi's formula. Okay? For the antipode, yeah.
One thing. So, just to make sure I understand everything correctly, this is not graded because delta doesn't necessarily preserve grade. Right?
That's right. So what I would like to say is just apply Takeuchi's formula. But Takeuchi's formula, we said, works if you're graded connected, which in this case we might not be because our posets might not be graded, or if the coalgebra is co-nilpotent. And if you check this, you'll see that this is not co-nilpotent either. But again, let me claim that the exact same argument that we gave to prove Takeuchi's formula works in exactly the same way here. Okay? The proof of Takeuchi works here. And there's really nothing new you have to do that. It's exactly the same argument. And so that means we can actually assert this, that sum n greater than or equal to 0, minus 1 to the n, m to the n minus 1, pi to the n, delta to the n minus 1 of p. Okay? This is the formula. And so let's just write down what this is, and we'll see that it's exactly what I wrote down here. Okay? So let me do this in 3 steps. So first of all, what is delta to the n minus 1 of p? Well, we talked about how you're just taking p and making it do exactly this, jump from x0 to x1 to x2 up to xn. Okay? So this is just the sum over chains like this. And then we get x0, x1, tensor, x1, x2, tensor, x n minus 1, xn, and
After
and that's right. So the picture that goes with this that you should remember is that our poset P looks like this, and if we apply the nth coproduct, then what we're doing is just looking at all the ways of going like this, taking some chain here, x1, x2, up to xn minus 1, and then xn is 1, and then x0 is 0. Okay? And we take the direct product, the tensor product of all these intervals, but we allow that some of these xi's might be equal to each other. Okay? That's what the formula gave, and so we get this. Okay? So that's the first part of the formula. Now, what is this going to do? So when we apply pi tensor n, we're applying pi to each one of these things. Okay? And again, remember that what pi is going to do is just drop off things that are in the graded case. What it does is that it drops off things of degree 0, and here it's going to do exactly the same thing. It's just going to kill off the elements of this form, such that one of the factors is a one element interval. Okay, so if any one of these things is a one element interval, then pi kills it, and the things that survive are exactly the ones where all of these guys are distinct. Okay, and so when I apply pi to the tensor n, what it does is that it takes away all these inequalities and it makes them strict. So that's what that does. And then when I apply n to the n minus 1, that just multiplies, it takes the tensor product, and it turns all these things into multiplication. Okay, and so what the green stuff does is that it kind of gets rid of the little circles around the tensor and just turns the tensor product into a direct product. Okay, and then everything else is the same. Okay, and so what we get here is exactly the formula that I wrote down. Okay. So, in other words, this is just Takeuchi's formula for incidence Hopf algebras. And the same proof we did for Takeuchi is going to work here. Okay? And so that's why I said that basically I was going to prove this to you, but we basically already did it. Okay? So do you guys have any questions about this proof? Yeah, let's.
Why, I guess, why do we need grading for it? Since we sort of didn't need it here. What does this have that is sufficient?
Yeah, that's a good question. So let's talk about what we proved Takeuchi's formula for graded things, and this is not graded. So what does this have in common with graded things, so that the proof does go through? So remember that if you were graded, that said that when you take the nth coproduct, that splits you into a bunch of things. And the degrees of those things have to add up to the degree of the original thing. And that meant that if you take a really, really high coproduct, then some of the factors have to have height 0, and therefore pi killed them. That's what we did for Takeuchi's formula. And here what happens is that when you take a fixed poset and you take a really, really high coproduct, then even if the poset is not graded, there's only so many steps that this can have. Until some of the intervals are trivial.
So you could define a sort of a weak grade that's like the maximal chain length or something, and you still have the same.
That's right. So even though this poset might not be graded, it does have a notion of height, which is the size of the largest chain. And if you take delta to the higher power of that, then one of these factors is going to be 0. Sorry, it's going to be a single element interval, and pi is going to send it to 0. Okay? And so that's what these two things have in common. So even though this is not graded, it's almost graded.
Any situation where eventually a large enough delta has to be 0 is going to actually give us
So if you remember I also argued that in the co-nilpotent case that if a large enough power of delta is 0, we were done. But here what we're saying is that if a large enough power of delta gives you constants, then pi kills them.
Okay.
Which is a little bit weaker, but so everything holds in that case also. Okay. Okay. So this is basically the proof, and what I want to do next is just show you that we can really get a lot of mileage out of this result. And let me just ask you guys, how many of you have taken some kind of combinatorics course where you talked about posets for more than a couple of weeks? So maybe, some of you. So one thing that I want to show to you over the next couple of classes is that posets are a really powerful place to work in, actually, and there's a lot of things that can be encoded in posets. Okay, and so what we're going to do right now is the following: we have this construction for an incidence Hopf algebra given a hereditary family, and so what we're going to do in the next couple of classes is come up with lots of examples of hereditary families. Okay, and for each one of those examples, we're going to get a Hopf algebra, and we're going to recognize some of the ones that we already constructed, and we're going to see some new ones. So that's my plan for the next couple of classes. So we're just going to do a whole bunch of examples of this construction. Examples of incidence Hopf algebras. So first, let me just get two very silly examples out of the way. So example 0a. I'm going to do two pretty silly examples. One, P is all finite posets. Okay, and this is isomorphism. So clearly that's hereditary, because if you take a subinterval of an interval, you get an... Sorry, what I mean here is all finite intervals, right? Because I need these things to have a 0 and a 1. All finite intervals. So this is clearly closed undertaking subintervals, and this is clearly closed undertaking products, because if you multiply two intervals, you get an interval. Okay, so this is an example. And the other silly example is that you consider all finite intervals, and you actually don't want to morph them if they're isomorphic. So I want to say that if two posets, they're isomorphic, but the names of these elements are different from the names of these elements, then I want to consider them different. Okay. And so this is where this issue comes up of what to do with a one-element poset, etc. And to be completely honest with you, I didn't think about this ahead of time, because I thought it was more trivial than it really is. Okay. So we're going to postpone this discussion to the forum of what exactly does it mean to be trivial, because the point is that I do want to identify posets that have one element, okay? And that is actually one of the conditions that I'm going to write down here. And I'll write these conditions in a minute, but let me just.
How does this creating a problem for epsilon if you won't creating a problem for u?
For you, that's what I was pointing to.
I thought you pointed at epsilon.
Oh, okay. Maybe I pointed at epsilon, but I meant to point at you. Yeah. Okay. But the point is that I don't want to identify posets if they're isomorphic. I want to keep them separate from each other, and so I do that in the most trivial way. And let's talk in the forum about what the most trivial way is, because I do have to identify posets that have only one element. But let's talk about more interesting examples. Okay, so let's talk about other families that are hereditary. So here's a family that's hereditary, and maybe I'll call it B. All finite Boolean algebras. Did I say this word already? Boolean algebra? I did show you it, but maybe I didn't call it Boolean algebra. So Boolean algebra, by definition, is a poset isomorphic to the poset 2 to the s, the poset of subsets of a set. Subsets of S under containment. Okay, so a simple example of this, if S is the set A, B, C, then the subsets of A, B, C are organized in a poset like this. Okay, and so this is the Boolean algebra B3. And in general, the Boolean algebra Bn is the subset, the poset of subsets of an element set. Okay. Let me declare my equivalence relation to be isomorphism. Okay. So let's think about why this is a hereditary family. Okay, so I need to check that it's closed under these two operations. So taking intervals. Bless you. Okay, let's take a Boolean algebra. Okay, there it is. You should think of this as all the subsets of the set S. Okay, and let's take an element inside of here. Sorry, let's take an interval inside of here. Okay, so what does that look like? Well, the interval looks like something like this, right? For some A and B, such that A is a subset of B. Okay? And so what I need to justify to you is that if the black poset is Boolean, then the blue poset is Boolean. Okay? And how do I do that? Well, what I need to do is show that the blue guy is isomorphic to the subsets of something. So what is it isomorphic to? The subsets of what? Of B minus A, right? So if I look at the subsets of B minus A, then I have an isomorphism from here to here, where you just take, every set here, and you add the elements of A, and you get the corresponding set here. Do we agree? Okay. So that means that Boolean algebras are closed under taking subintervals. That's okay. Okay. Now I need to justify that this is closed under taking direct products. Okay, so let's take a direct product of subsets of A and subsets of B. Okay, so I take the direct product of this thing, and remember the way we do that is that we kind of take the black poset, and at each element we put a copy of the blue poset. Okay, and so we get something like this. Maybe I'll make this skinnier to make this picture a little bit clearer. So at each element of the black poset, I put a copy of the blue poset, right? And so I get something like this. And correspondingly, at each element of the blue poset, I have a copy of the black poset, and so I get something like this. Okay. This is the product, and I have to justify that this is Boolean. Okay. So what is this isomorphic to? The subsets of whom?
I think it's not actually, I don't think you actually have A cross B there. I think you have subsets of A cross B there.
Well, so, sorry, I meant to write something different. I meant to write that if this is 2 to the A, and this is 2 to the B, then the poset that I want here is their direct product. 2 to the A times 2 to the B. Okay? What is this isomorphic to?
2 to the A cross B.
2 to the A cross B, are you sure? Should be 2 to the something. Now, I mean, one way of knowing is, let's just count elements. How many elements are there here? Let's say A has m elements and B has n elements. How many elements do I have here? 2 to the m. How many elements do I have here? 2 to the n. How many elements do I have in a product poset? It's the number of elements here times the number of elements here. 2 to the m times 2 to the n. So the number of elements here is 2 to the m plus n. And therefore, this should be the subsets of a set of size m plus n. And so it should be like A union B. So let me a little bit carelessly write A union B, and then we'll see. So why am I being a little bit careless?
Because they might share elements.
Because they might share elements. So, but that's not really a big deal, because it doesn't really matter what, I mean, what matters with a Boolean algebra is what the size of the set is. And so we can just choose A and B to be disjoint. That's not a problem. Okay? And as long as A and B are disjoint, I claim that this is an isomorphism. Okay? So in other words, the claim is this. Okay. Yeah.
What was wrong with A times B? What was wrong with the direct product?
Well, so the question is, why is this not 2 to the A times B? And one answer is that it has the wrong size, so that means that they can't be isomorphic. And this has 2 to the m plus n elements, and this has 2 to the mn elements, and they can't be isomorphic. Because A cross B has mn elements. And so this would actually be a lot bigger than it needs to be.
A tensor B has m plus n. Like, I feel like they were reversed, right? Like, when you have tensor, they're multiplied, and when you have direct product, they're added. Am I mistaken?
We're taking sets here, right? And so I'm talking about two things: the disjoint union of two sets and the direct product of two sets. Since we're going to spend the next little while talking about posets, I think this is a good exercise for you guys to do. And so this is going to be one of the homework problems: is to prove this isomorphism. Okay. And once you prove that isomorphism, then you will have proved that this is closed under taking direct products. So this is a homework exercise. Okay. So, by the way, let me make a comment that I think it's in the air, so I might as well say it. Homework 3 was a little bit brutal, and I decided homework 4 needs to have some more accessible questions than homework 3 does. And so, that's an example of a more accessible question that I think homework 3 didn't have. Okay. I mean, I told you this class was going to be hard, but homework 3 I think was a little bit too hard. You haven't complained to me, but I agree with the feeling. Okay, so this is closed under taking subintervals. It is closed under taking direct products. So this is a hereditary family, and therefore we have a Hopf algebra. So let's try to identify what this Hopf algebra is. See if we know it or if we don't know it. Okay. This is always what you should do when you encounter a new algebra, a new Hopf algebra. You should say, is this new or did I know it already? Okay, so let's try to figure out what is the underlying incidence Hopf algebra. So let's take B mod equivalence. Okay, so what is B mod equivalence? What are the different equivalence classes of Boolean algebras? I'm sorry? The B sub n's, right? So now you should notice that here I define these to be finite Boolean algebras. And so that means that we want the B sub n's for n finite. So n is some natural number. Okay. And so therefore, H of B is, at least as a vector space, it's the span of these things, right? So it's the span of B0, B1, B2, etc. It's a vector space. Now, let's try to figure out what is the product structure. Now, if we can find the product with respect to this basis, then we will know how to multiply any two elements, right? And so let's try to take the product of bi and bj. What do we get when we do that? It's kind of what we're saying here, right? So we're taking the direct product, and we're saying that the direct product of bi and bj is bi plus j. You should notice that this is a lucky circumstance, that when you multiply two basis elements, you get a basis element. There's no reason for that to be true in general. Right? For most algebras, if you multiply two basis elements, you're going to get some weird thing. But here it happens that when you multiply two basis elements, you get a basis element. What about the coproduct? Let's go over there. Let's not try to squeeze it in here. So coproduct so we need to sum overall. We need to, we have the Boolean algebra Bn, and we need to sum over all elements of the poset this times this. Right, so we need to sum over all elements of the poset, all subsets of set from 1 up to n, and we get 0, A, tensor, A, 1. Okay? And what's this? What is 0A? Well, this is just the Boolean algebra on A elements. Right? And what is A1? It's the Boolean algebra on the other elements. Right? You should notice that here I'm being a little bit loose with the notation, so it doesn't get really messy. Really, when I write something like this, I mean an equivalence class. Right? I mean, this is a poset, and so if I wanted to be very careful, I would say equivalence class, and I'm calling that equivalence class Bn. Okay. So, is there a simpler formula for this? Well, yes, because there's a lot of terms that are equal to each other here. Whenever two sets A have the same number of elements, they give you the same contribution, right? And so what I'm going to get is terms of the form bk or bi tensor bj, where I plus j add up to n. And how many times does this appear? The number of times that I have subsets of size I, which is, choose I. Okay? And so this is our coproduct. We can write it like this. Or, actually, let's just write it as bi tensor bn minus I from I equals 0 to n. So that's the coproduct. Let's do the, well, let's get the unit and the co-unit out of the way. So what's the unit? The unit is the one element poset. So what is the one element poset called here? It's B0, right? The subset of the 0 element set, that's the 0 element set. The empty set is the only one that has only one subset. So U of 1 is B0. And what is epsilon of Bn? Well, epsilon of Bn sends me to 1 if I have one element and 0 otherwise. So I get 1 if n is equal to 0 and 0 otherwise. Okay. Do you recognize this Hopf algebra? I'm sorry? It does look familiar, right?
Probably be related to the one on polynomials or something like that.
This is graded, right? For sure. Because if we say that bi has degree I, then degree I times degree j is degree I plus j. And degree n gets split into things of degree I and degree n minus I. So Seth, you're telling me that this reminds you of a polynomial ring. In fact, which polynomial ring? K of x. So if you think, if instead of bn I had written x to the n, what would I get? My algebra as a vector space is the span of 1, x, x squared, etc. Product, x to the I times x to the j is x to the I plus j. Coproduct, delta of x to the n is the sum of n choose I, x to the I, x to the n minus I. So what we have here is exactly the Hopf algebra k of x. You see it, right? So the fact is that the Hopf algebra of Boolean algebras is isomorphic to k of x, where k here is just whatever k we're using. Here I'm defining this to be the span, right? And so the span is the span over some field, and whatever that field is, we're going to get this. Okay? Yeah.
The argument you just made by pointing at base and saying, look, this looks the same, is that sufficient?
So we need a proof, right? And what's the proof? Well, it's basically doing what I just did, but in math words, right? So what's the word? What's the word we need to use here? Well, you just need an isomorphism that preserves the structure. So the isomorphism is the one that takes Bn and sends it to the n. And then we need to check the respective structures, which is what I did. Right? I said, you know, x to the a times x to the j is x to the a plus j. So we need to check this as an isomorphism, and that's essentially what I did. So, but I mean, yeah. So in principle, there's a lot of things to do. You have to check it preserves sum, it preserves multiplication under scalars, it preserves product, it preserves coproduct, it preserves unit, it preserves co-unit. But basically, the way to say that is to say, look, it's the same generator, same relations. So that's clearly an isomorphism. Okay, so I did everything except that I haven't written down the antipode, right? So what is the antipode? Well, we already computed the antipode of this thing, and we did it twice. One time, we were clever, and the other time, we were not clever. Would plugging into here be clever or not clever? Not clever. What would we get? We would get exactly what we got last time, right? We would get the formula that Takeuchi gives us. And so this is an example where the formula you want is not this one.